Okay, great. So we can start the morning's events. I'd like to introduce the first speaker, Professor Merkurjev's work over many decades in algebra and a very broad, extremely broad range of algebra has been widely influential for decades, from before his 1986 talk at the International Congress of Mathematicians to his 2012 award of the Cole Prize in Algebra by the American Mathematical Society to today.
Well, thank you very much. Thank you for the invitation. So I'm going to speak on the essential dimension, which was initiated, a study on the essential dimension was initiated by Bühler and Reichstein. And roughly speaking, essential dimension measures complexity of an algebraic structure. It is equal to the smallest number of algebraically independent parameters one needs to find the structure. So more precisely, but still not quite, let's take a class of algebraic objects. I will explain what it is in a minute. Algebraic objects and class. And the essential dimension assigns to a class of algebraic objects an integer, just one discrete parameter, some integer called the essential dimension. If A is the class of algebraic objects, this is the essential dimension of A, non-negative integer. And the main property of this parameter is the following. Suppose you have a surjective surjective map of two classes of algebraic objects from A to B. Then the essential dimension of A is greater or equal to the essential dimension of B. So the complexity of the first class is greater or equal to the complexity of the second class. And the application of this property is as follows. Suppose we are given class B of objects and we would like to parameterize this class. So we find the conjectural list of parameters, that is A. So those are parameters, which can be considered also as a class of objects. And we have a map from A to B. For every set of parameters, you have an object in the class B. And, well, we would like to prove that this is a surjective map, that B is parameterized by the list A. And instead of just studying this proof or try to disprove the statement, there is a test on the essential dimension. You compute the essential dimension of A, if possible, and the essential dimension of B, and compare the two numbers. If essential dimension of A is less than essential dimension of B, then of course such a surjective map from A to B cannot exist. So that's the first test, which disproves a parameterization conjecture. That's how essential dimension works in general. Now, before starting a real proof of the essential dimension, let me give an example. Well, let F be a field. It's a base field always. Should be given, and for example, if F is a field of complex numbers, and then we consider all extensions of this field F, not necessarily finite extensions, K, and let us do the following class. Q of K is a set of isomorphism classes, iso classes, of quadratic forms over K of dimension some fixed number m, and should be also a given integer. So every form, quadratic form, looks as follows: Aij xi xj, summation from 1 to n. So every quadratic form can be given by n squared parameters. So we can say that the essential dimension of this class is at most n squared. But of course, one could do better. You can make this matrix Aij symmetric. So roughly, we need just n squared over 2 parameters. But one can do even better. We know that every form after some linear change of variables can be written as a diagonal form. Well, say bi xi squared, where we need only n parameters up to isomorphism. So essential dimension of this class is at most n. And in fact, one can show that it's the best you can do. You cannot make number of parameters smaller than n, and then the essential dimension of this class is equal to n. Complexity is equal to n. Okay, how can one rephrase this? So given quadratic form Q over a field K, so in other words, the variables, the parameters in K, we can consider a smaller subfield, namely K prime, generated by over F by those BIs, B1, Bn. And we can say that Q is defined over that smaller field K prime, because those diagonal terms belong to K prime. And in other words, Q of K, where we have our element Q, is connected with Q of K prime by the obvious map. And our form Q comes from a form, well, given by that diagonal presentation. And K is much smaller. K is generated by n parameters, elements of the field capital K, and those parameters could be algebraically dependent or independent. But in any case, the transcendence degree, the largest number of algebraically independent generators of K prime over F is at most n. So the idea is to measure the essential dimension by the transcendence degree of the field of definition. K prime is the field of definition of Q, and we take the smallest possible transcendence degree. Well, now we can move to the formal definition of the essential dimension. So first of all, what is an algebraic structure? What do we want from algebraic structure? First of all, we fix a field F. And then for every field extension, we are given a set A of K, set of objects of particular type. In our example, is the set of isomorphism classes of quadratic forms of dimension n. Then we need to have the following property for any field isomorphism from K to L. We should have a map from A of K to A of L. It's like any quadratic form of the smaller field over the smaller field can be considered as a form over larger field. And of course, this collection of maps should be compatible with the composition. Well, such a structure in algebra is known as a functor. A from the category of field extensions over F to a category of sets. But we will call A an algebraic structure, class of algebraic objects. Now, how to define essential dimension of that class A, or the functor A? You pick any K, you pick any element in the set A of k. We first defined the essential dimension of that particular element A. So we consider fields k prime smaller than k, while still containing f, all fields contain f, such that A is in the image of the map from A of k prime to A of k. It's like in our example, our quadratic form comes from a form from smaller k prime. And then you say that k prime is a field of definition of A. And then essential dimension of that element A is, by definition, the minimum of the transcendence degree of that field, k prime over f, taking over all fields of definition of A. K is a field of definition or definition of A. Let's see some number computed for any particular element A, and then finally the global essential dimension of the class is the maximum, the essential dimension of A for all A elements of all sets A of k for all fields k. So that's the formal definition of the essential dimension. It could be finite or infinite. The most interesting case is finite. And I would like to give a couple of examples. First, algebraic variety. X is an algebraic variety over field F. Then you know that for any field k over F, you can compute the set of points of x over k. If x is given by a system of for polynomial equations, then x of k is the set of solutions over the field k. And you see that x is an algebraic structure. And it turns out that the essential dimension of that functor, that algebraic structure, x, is nothing but the usual dimension of the x. So complexity of the algebraic variety is not just its dimension. That is because every point in that set is defined over the field, residue field of x. And in fact, the residue field is the smallest field over which that point is defined. And then transcendence degree of the maximal transcendence degree of such fields, by definition, is exactly the dimension of x. That's the first example. The second, let's do all matrices over a field k of size n by n. What's the complexity of this class? Of course, it's a set of points of a fine variety of dimension n squared. So the essential dimension of the class of matrices n by n is n squared. But what about the quotient of this? You consider the class A, all matrices, modular conjugation. What's the essential dimension of this class? Should be at most n squared, but in fact it's less. So we know that every conjugacy class of matrices contains a unique so-called canonical form, which is matrix of this shape. It is a matrix of ones below the diagonal, the other elements 0, besides the last column where you can get anything. And so we have n parameters of the size of this matrix n by n. to define such a rational canonical form. So we see that the essential dimension of that class of matrices modular conjugation is at most n. But on the other hand, we have a map from A to the affine space of dimension n by taking every matrix, say A, to the coefficients of the characteristic polynomial of A. We have n coefficients. This map is well defined because conjugate matrices have the same characteristic polynomial, and this map is, of course, surjective. Every polynomial can be characteristic polynomial of some matrix. So, by the main property of the essential dimension, we have the inequality essential dimension of A is greater or equal to the dimension of an, which is n. So we got the upper bound and lower bound, and they match. It's very rare, but possible case when we really can compute the two, the essential dimension that is equal to n. In fact, in most of the cases, we compute the essential dimension this way. We try to find an upper bound and lower bound. And if they match, then we are done. It doesn't work always, but in some cases it works. Well, very interesting functors, very interesting algebraic structure arises from algebraic groups. So suppose G is an algebraic group. So it's a group and algebraic variety at the same time, over F, given by polynomial equations over field F. We can consider the functor of torsors. Torsors G, G torsors of K is just the set of isomorphism classes of G torsors over K. What's the G torsor? It is a variety on which group G acts simply transitively. And the essential dimension of this class is denoted like this. It's called the essential dimension of the group G. So essential dimension of an algebraic group measures the complexity of the functor of torsors. Well, many nice example, classical example are in this setting. Let me give you a standard example. Let's take an algebraic object. Usually it is vector space together with additional data like algebra or quadratic form, cubic form, and so A, it's over some field K, F, over F. And suppose we can extend the field, for example, tensoring the vector space with the larger extension. So for any field extension K over F, we have an object AK over larger field K. Now, an object B over A over K is called a twisted form of A. If if B and AK are equal over an algebraic over separable closure of K. Now, if you have a twisted form B of A, then you can consider the set of isomorphism classes between B and AK. And we also can consider the automorphism group of A, and usually it is an algebraic group, so let's call it G, and then G of K, this group of points over K, acts on the isomorphisms, set of isomorphisms in the obvious way, and usually that set also has a structure of an algebraic variety, and of course this action is simply transitive. Every two isomorphisms between B and AK are, well, differ by an automorphism of A. So it's a torsor, it's a G torsor. So every twisted form of A gives you a G torsor, where G is the automorphism group of A. And in many cases, the converse holds. Every torsor for the group G is isomorphic to the variety given by this construction for some, in fact, unique twisted form B. So you can say that the essential dimension of G is the same as the essential dimension of the class of twisted forms of A. Isomorphism classes of twisted forms of A. Well, here are the two classical examples. You have first as an object, the algebra of n by n matrices over F, that is small a. The automorphism group, which is G, is the projective linear group of A over F of size n. And what is the twisted form of Mn of F? Mn of F is an algebra which is central. Center is the group of scalar matrices, algebra of scalar matrices, and it is simple. It has no trivial two-sided ideals. The same property should hold for all twisted forms. In fact, twisted forms are exactly of this form. Central simple algebras. So the essential dimension of the projective linear group is the same as the essential dimension of the class of central simple algebras of dimension n square. N is called the degree of the algebra. That's first example. And the second example, let's take for the algebraic structure A, the product of n copies of n some fixed number of the field F. What is the automorphism group of this structure? It's just the symmetric group Sn, permuting the components. What is a twisted form? The twisted form of such an algebra is a separable algebra. What is a separable algebra? It is an algebra of L over F, dimension n, and separable, it is of the form f of variable x modulo some polynomial, well, ideal generated by polynomial, which is a monic separable of degree n. It could be a field in particular. But in general, it's just the product of several separable field extensions, total degree n. Therefore, the essential dimension of Sn is just the complexity, essential dimension of the class of such separable algebras of dimension n. Well, this is a very interesting example, and I would like to give some details. Many questions are open here. Also, the setting is very elementary. So what is essential dimension? Our general answer is not known. How can one rephrase the problem? So you see that every algebra is certainly determined by the coefficients of the polynomial f, and there are n coefficients. So clearly the essential dimension of Sn is at most n. How do we get this polynomial f? You take the generator of the algebra L, and f is the minimal polynomial. Well, a polynomial which vanishes on the generator. But what if you take another generator? Of course, you get another f for the same algebra. This new f can be simpler. In fact, you can do things simpler. You can make an easy linear change of variable to eliminate the coefficient xn minus 1. We change x to x plus a for some parameter a. So you see that the essential dimension of Sn is at most n minus 1. Well, if n is at least 2. And in fact, if n is at least 3, you can even do better. If you take this polynomial, monic polynomial, look at the last two coefficients, say bx and c. Scaling x, multiplying x by a scalar, you make those equal. So you lose one more unit, and can state that essential dimension as n is at most n minus 2 if n is at least 3. Well, Reichstein proved that essential dimension of Sn is at most n minus 3 if n is at least 5. On the other hand, there is an lower bound as follows. Sn, a symmetric group, contains the product of several copies of z mod 2z. How many? You take k, the integer part of n over 2. Essential dimension of a larger finite group is greater or equal to the essential dimension of a subgroup. And z mod 2z itself, just one copy of z mod 2z, has essential dimension 1, because what is to give a z mod 2z extension? Just quadratic extension of a field. And to give a quadratic extension, you need just one parameter. And here we have k parameters. So in fact, this essential dimension is equal to k. So we have inequality essential dimension of Sn is at least this integer power. Combining the two types of inequalities, we get the following precise solution, values of the essential dimension for some small n. That is n. That is the essential dimension of Sn. 1 is 0. S2 is cyclic of order 2, 1. For degree 3 extensions, need only one parameter still. You see the equation, cubic equation can be reduced to this form, ax plus a. Only one parameter needed. For degree 4, it's 2. 5, still 2. 6, 3. And that's the best you can do from the two inequalities. For 7, it is either 3 or 4, but then some very elaborate things from algebraic geometry for cubic, for degree 3, dimension 3 varieties allowed to prove that for 7 dimension is 4. It's due to Duncan. And that's all known. Well, this problem can be stated in very elementary terms, and it is still very strange that the answer is not known. So let me give you a couple of equivalent formulations of the essential dimension of the symmetric group. Well, first of all, the essential dimension of Sn is the minimum of the transcendence degree of k prime over k over f. By the way, it doesn't depend on the ground field f, at least for those small values, and probably should not depend. Always, what is k prime? K prime is an intermediate field between f and the field of n of rational functions in n variables. x1, x2, xn are variables, and symmetric group acts on that field by permuting the variables, and intermediate field k prime should be G invariant, and G acts faithfully. Otherwise, you can take F acts faithfully. That's one definition. Of course, it's not so easy to understand how all these subfields K prime look like. Well, the other one is looks even more elementary. So we take all a function, a rational function, say phi from the field generated by x2, x1, x2, xn, rational functions in n variables. Such function may not be, of course, symmetric, and in fact we take the one which is not symmetric, and we apply sigma for all sigma from the symmetric group to the function phi. We get a finite set, and we would like to have this set so that the group, symmetric group Sn, acts faithfully on this set. It is not really a very strong restriction, because the kernel of any action should be a normal subgroup in the symmetric group. Sn, if n is at least 5, Sn has very few normal subgroups, is a trivial group or alternating group. So we just need to have that set not stable element-wise by the alternating group. So in other words, phi should not be stable by this alternating group. Well, actually every phi randomly taken should satisfy this property. And then you generate the field over f, over ground field, by all such functions for all sigma in the symmetric group. And then you compute the transcendence degree of this field and take the minimum. Minimum over all phi is the property I described. So you need to find a function which is, well, not really symmetric, and such that this transcendence degree is as small as possible. So we have more and more sufficiently many algebraic relations between those functions sigma or phi. For example, if you take the following function phi, x minus x1 minus x2, x3 minus x4, x1 minus x3. It's called cross section. Then, if n is at least 5, then on the right-hand side here, you get the minimum, well, the transcendence degree for that particular function is equal to n minus 3. That's exactly how one gets this upper bound n minus 3. And, well, I think most of the people believe that that's the best you can do. So this function provides the minimum, but that is not available. The proof of this is not yet available. Okay, maybe one last thing, still related to an algebraic group G, when we want to compute the essential dimension of G. One can get an upper bound as follows. You have, let's take a generically free representation of G. Say vector space V of finite dimension of G. Generically free means that the generic stabilizer of any vector is a trivial subgroup. Of course, it can be trivial for all vectors. Zero vector has non-trivial stabilizer, but most of the vectors have trivial stabilizer. And in fact, in this case, there is an open, non-empty open subset invariant under G such that G acts freely on U, and one can form the variety U mod G, and this canonical morphism is G torsor. G torsor. Well, that is over F. Now you take any field extension, K over F, and you consider a point over K. A point over K of that variety, U mod G, is a morphism from spectrum of K to U mod G. And take the fiber product. Well, this is a G torsor. And remember that this thing belongs to the structure we denoted G torsors over K. And we started with the points of U mod G over K of K. So for any point, for any morphism from the spectrum of K to U mod G, we have a torsor E. We have this map of two structures. One is variety, the other one is, well, the structure stated with a group G. And the thing is that surjective map. The torsor U over U mod G is called so-called versal. Every other torsor is a pullback of the versal torsor. In particular, we get the essential dimension of the group G is at most the dimension of the variety U mod G, which is, of course, dimension of V minus dimension of G. So if you find a generically free representation, of the group with some small dimension of V, you get some good upper bound for the essential dimension of G. Unfortunately, it doesn't give the precise value. Let's go back to the example when G is S3. We know that essential dimension of G is 1, but G has no one-dimensional representation which is generically free, which means faithful for finite groups. So there is no faithful character, of course, of G. So in many cases, dimension of G is, essential dimension of G is smaller than the minimum of all differences dim of V minus dim G. this thing. But there is one instance when we have the equality, and it's the last statement I would like to give you. It's a theorem by Karpenko and myself. Well, if G is a P group for some P, and then the essential dimension got frozen. Okay. Then the essential dimension of G is equal to the minimum of the dimension of V, where V is a faithful representation of G. So, of course, the dimension of G is 0 in this case, and we have exactly the equality given by the upper bound, which allows us to compute the essential dimension of P groups. Okay, I should stop now. Thank you very much.